So it's an honor to be here presenting you the Higgs to tautau analysis in CPC. Since we are out of time, I will. Yes, I think he needs something or not. He needs you or me? Okay. Yeah. So at first I will try to present what I have done in the tau finding in CPC for different channels, and then there will be a comparison between the CPCV1 and the new detector and at different center of mass energy. First of all, we need to know why we need to study the Higgs to tautau channel. As a lepton, the tau have heavier mass, leading to a larger coupling constant to Higgs. And among the heavy fermions, the decay mode of the tau is similar than the other fermions. And the performance of the tau finding relies on the particle separation, which is related to the detector mode and also the reconstruction. And that makes this channel a nice testbed for the detector and also for the reconstruction algorithm. So first of all, what I have done is that, as shown here, the topology for the channels where the Higgs are produced accumulated with a pair of leptons, and also for the channels where there are two jets, the topology are different. That's why we use the two different strategies for these two kind of channels. And all the studies have been done for the 5 inverse antibar samples simulated with MOCA and reconstructed with ARBO. For the lepton Higgs channel, I chose the mu Higgs channel to present. And for the steps are shown here. First, because of the computing resource limitation, we always use a pre-selection before the full simulation in CPC. And then for the tau finding, the idea is that the number of particles are less in tau events. And after we have the Higgs to tautau events, we use the impact parameter to reduce some of the irreducible background. For the pre-selection, the assumption is that our reconstruction algorithm is highly consistent with the simulated particles. And this has been studied by a series of performance, and which I will not introduce here. And in the mu Higgs channel, the pre-selection applied is that there exists a pair of mu's, of course, and the invariant mass and the recovered mass of this pair of mu's should obey the mu Higgs channel. And after this pre-selection, we can see that most of the background, standard model background have been reduced by a large factor. And then once we have got the mu Higgs events, what we have to do is first to veto the pair of mu's decayed from Z by using their invariant mass, and then we separate the whole space into two regions, and by counting the number of particles in these two regions, and also to calculate the angles between the furthest track to the leading track, and also the furthest photon to the leading track, and also the furthest photon to the leading photon. And all these parameters are trained in TMVA. Here is the distribution of these parameters, the number of tracks, the number of photons, and also the angles. The distributions of the signal are shown by the blue and red line, which is the simulated information and also the reconstructed information. We can see that they are consistent with each other. And then these parameters are trained are trained in the TMAA. And if we see this plot, we can see that there is a peak for the background, which is Higgs decaying to WW and WW leptonic decay, and even WW decay to tautau, and that's not easy to distinguish with the signals. And then we used the impact parameter to reduce this background, since the vertex of taus are further than the prone leptons. And here, if we draw this distribution of the impact parameter for the signal and for the background, we can use it to fit the signal strength of in the mu Higgs channel. And the accuracy we got here is roughly 2.2%. And the similar study can be done in E Higgs channel. And it's not done, but we simply extrapolate it to the E Higgs channel. And for mu Higgs channel is also similar, but we don't need to whittle the pair of neutrinos. And the background, if we look at the background here, it's too large comparing to the signal, which makes it rather tough to fit. So we show only the statistical errors here, which is 5%. And now we have finished the easier cases. And here comes the main course, which is the QQ Higgs channel. First is also the pre-selection. I'm not going to present it here. And in the QQ Higgs channel, what is done is first to find the tau candidates among all the space, and then once we have chosen the pair of taus decayed from Higgs, we use the other particles remained to be the QQ Higgs system, and this system, the information in this system are also used to reduce the background. And at last is still the impact parameter to fit the number of event and number of background. So the tau candidate, how we find the tau candidate? The strategy is to define the two coins around the energetic tracks around among all the space. And by the parameters used in this tau finding is that the number of particles in the small coins, the invariant mass in these coins, and also the energy ratio between these two coins, which is the isolation condition. As shown here in taus, it's rather isolated from the other particles, but for the jets, the ratio in these two coins should be less than in taus. And all these parameters are optimized to the efficiency times purity. And once we have at least a pair of opposite charged taus, what we do is to choose the pair of taus with the leading energy, and all the other particles are treated as the QQ systems. In this way, we can use the invariant mass of the tautau system, the invariant mass of the QQ system, and also the recall mass of the QQ system. Now I'm going to present these three parameters in detail. First, for the invariant mass of this tautau system, we use it to reduce the background where the taus we found is not really taus, but fake taus. So their invariant mass should not be in our signal region. And for the QQ invariant mass, we can see the signal should peak at the mass of Z, but for the Z Higgs conjugation background, as shown here, the peaks at the mass of Higgs. It's obvious. And after the previous step, most of the background remaining as a background with the same final state particles as our signal, which is QQ tautau. And this background can be reduced by using the recall mass of the QQ system, since the recall mass of ZZ to QQ tautau should be peak at the Z mass. And in this way, most of the background remains after this step are really irreducible, and then we use the impact parameter to get rid of these particles. And in this channel, we have reached an accuracy to less than 1%. And here is the combination of all the channels, and the final combination is 0.8%, which is really nice. And then I switched to the new model and a different center of mass energy, as have been already shown by Manchi's slide. Here is the difference between CPCV1 and PODIS. And we are all familiar with this cross-section, and we know that at 240 GeV, there are less signal and more background. So in the mu-mu-Higgs channel, the similar studies have been made with the signal have been been studied with full simulation, but the background extrapolated from the 250 and just by a simply extrapolation to 240 GeV. But the accuracy have been better, because if you remember in CPCV1 at 250 GeV, the accuracy was 2.26. And this is because, by some reason, the distribution of the impact parameter are sharper than in 3.5 Tesla, and this is still under study. And here is the distribution of the parameters used in the QQ Higgs channel, and as well as their cut efficiency for each step. Here the cuts are not optimized in this study, because we applied exactly the same cuts as in CPCV1. And here is, I should apologize for this typo with QQ Higgs accuracy. This degrading is not only because of the signal statistic and the background statistic, but also the cut efficiency as shown in the previous slide. And here comes my summary. I'm on time, I think. In one word, we have defined tau finding algorithm with high efficiency and purity. And thanks to our PFA-oriented detector, we can use the QQ system information, and also we can use the impact parameter from the vortex detector to get a better accuracy. And as shown here, the comparison between the CPCV1 and the PODIS at two different center of mass energy, there is less than 8% of degrading on the accuracy, which I suppose should be acceptable. Okay, so that's all. Thank you very much. And yes, please.
Thank you very much.
There is
there is already a hand up.
Can you go to slide 11, please?
11?
Yes.
Yes.
Okay, for my own curiosity, I mean, the pull is
yes.
really a log normal distribution.
Sorry.
So the pull function or the residual
yes.
is actually a log normal distribution.
Here I use the D0 squared plus D0 squared, but the sigma are similar to each other
But
here.
it's a sign input parameter?
You
If
mean
it
the
is a
sign? No, it's square. There is no sign.
You sign, there is no sign, so
Yeah.
you're not signing the input parameter.
No.
Okay, so maybe you can also consider signing it as we used to do in lab, and then you get, an easier distribution. You don't need to go log normal, I believe.
Yes.
Okay.
Yes, I have possibly a very, very naive question, though, because I'm kind of confused where you're using two different algorithms, and this one seems to be better than the other one. But I don't know if I'm mistaken or if you only have one tau reconstruction. It seems you're doing two different things in the case of the mu or the neutrino and then the jets.
Yes, because...
Can you explain?
Yeah, that is because as it's like in this plot, in the lepton-lepton Higgs channel, it's easier to whittle the pair of leptons. But in the QQ Higgs channel, it's not easy to whittle the pair of jets. That's why we need the cone-based algorithm to choose the tau candidate.
So the only difference is that in one case you have a cone and in the other one you don't?
Roughly, yes, because
Roughly?
in these events, what we do is just, after whittling the pair of leptons, it's just cut the space into two, and that's all.
It's an hemisphere, yes.
Yes.
That I understand. But it was the specific tau reconstruction, if then is different or not, because your efficiency seems different by a lot in the end.
Yeah.
And so I'm just surprised, because in principle, the tau ID itself should be the same.
Yeah, the tau ID is...
Actually, we take the advantage of the E plus E minus with no jet, where you really just have a few, So then this hemisphere algorithm can basically work, but not really in the jet environment. In the jet realm.
Yeah, so it seems to me that it's not really the tau ID, it's the overall background that are influenced. I mean, you're convoluting two things in the same... Right. Right, okay.
Yes,
Okay,
please.
thank you.
Sorry, again, I'm interested in extensions, but is the work going on into separating the taus by tau decay mode and working towards CP violation?
Yes, in CP violation will be the next step. We will separate we will apply directly the tau fender as in the QQ Higgs channels. We will apply this tau fender in the Z-pole maybe, and we will separate the decay mode, different decay mode of the taus, and to study the CP violation. It's the next step. Yeah.
Okay, let's thank the speaker again.
Thank you.
Thank you very much. It's always good to have people actually doing analysis and describing details. So we finish with the